Hi everyone, I'm Fraser Cain. I'm the publisher of Universe Today. I've been a space and astronomy journalist for over 20 years, and this is our question show. Your questions, my answers. Now, as always, wherever you are across my channel, if a question pops in your brain, just write it down. I'll gather a bunch of them up and I will answer them here. We record this show live every Monday at 5 p.m. Pacific time. So if you want to join the conversation live, I don't know what the questions are going to be in advance. It's all recorded live. You can ask follow-up questions, join the chat. It's a lot of fun. Come do this every Monday at 5. But I also gather up a bunch of questions that you've posted in the YouTube comments. So wherever you have questions, even in your dreams, I see your questions and I will answer them here. Now, you're going to see some codes in somewhere on the screen. Chad makes a hilarious joke about where it is. And those codes are a chance for you to vote on what you thought was the best question, best answer of the week. So go ahead, write down the question that the special code, the planet in the Star Wars universe that you thought was the best question answer, and I will tabulate them and I will mention them. So just make a comment. Just put in just the code if you want, or just like as part of your question, whatever works for you. So last time, the winning question was for Kevin Sullivan for Alderaan, asking, what do you think are the biggest misconceptions people have about telescopes looking back in time? And I believe I then went off on a rant about how I am aware that when you look through telescopes, you're looking backwards in time. And so when we say that something happened, it actually happened in the past. I guess people enjoyed my response. So anyway, congratulations, Kevin. Congratulations, me. We made a great team. Now let's get on to this week's questions. Bobo Logic. Normally your videos are informative, concise, and on topic, but this time you were too preachy and very sarcastic with your attack on the American public who think all astronomers are way overpaid and underworked, but are not solving any real-world issues, just spending hundreds of billions of dollars for pictures of places that we will never visit. Instead of telling folks that they are wrong, show some real-world results for money that could feed the poor, etc. So I think this question came from the response that I gave where people were concerned about James Webb. Underimpressed, not impressed by the results that are coming out from James Webb. And there's a lot of science that gets done all the time. When you think about various labs that are going on, people are studying the biology of different kinds of animals, or psychology, or economics, or a lot of basic research into physics, chemistry, organic chemistry. Like a lot of science work gets done. But one of the kinds of science that also delivers some really pretty artistic pictures is astronomy. And that is like the side effect of what they do. Like when an astronomer takes a picture of a galaxy to understand the composition, to try and figure out the chemicals that are in that galaxy, to understand where it formed, when it formed, etc. It's also a really pretty picture of a galaxy that we can totally share and ooh and ah about. But at the heart of it, it's a science instrument, and the scientists are the ones who are working with the technology. But like, I get this response a lot about, like, why are we spending all this money on the James Webb Space Telescope when we could be feeding the poor, or we should be fixing the environment, or anything? And like, that is a fallacy, because you're kind of saying you've got $20 billion to spend on NASA for the year, or you could spend that on feeding the poor. Which one is it going to be, right? Oh, we're going to spend that money on NASA, therefore we hate the poor. And that's a fallacy. That is not how it really works. How it really works is we've got $1.5 trillion that we want to spend on the military, and we're going to buy aircraft carriers and F-35s and cruise missiles and nuclear missiles. We've got money that we're going to spend on disposable styrofoam packaging and plastic bottles, and that's billions of dollars. And we could spend that money on plastic packaging and so on, or we could spend money on the poor. Any amount of money could always be spent on the poor. But science is one of the only things in our society that it's an investment in our future. And in some cases, it's very clear an investment. You can invest in therapies that can reduce the effect of malaria, and you can have a very real effect on the health and safety of people around the world. But we do other kinds of research that we don't know what the results are going to be. The benefit of researching into optics and lasers might not show up for 50 years, but suddenly there's a laser in everything. It makes our lives dramatically more convenient, healthier, safer, etc. And when you look at our modern society today, where the amount of poverty is lower than it's ever been, the amount of war is lower than it's ever been. I know there's an invasion of Ukraine, but still the total amount of war. But anyway, there are all of these facets of society that you can objectively measure that are moving in the right direction. And a lot of these come from the results of science. And we just don't know in advance which ones it's going to be. If we invest in the technology to build a really powerful space telescope, and that space telescope's helped discover an asteroid that has the potential to crash into Earth, well, that was money well spent. But what if you spend that money and you don't discover an asteroid that's going to crash into the Earth? Was that money that was poorly spent? I mean, obviously I get a little annoyed at that argument, because I always think that if you're going to think about how money gets spent, you have to think about it holistically. Every possible penny. How do we spend that? And the reality is that we all spend money in ways that are not always benefiting all humanity all the time. Every one of us makes these choices personally all the time. And we could make a better audit of how we spend money. But if I had to pick of all ways that we could spend money, science would be the last thing that I would cut, because it provides this lasting, ongoing benefit that grows and grows and grows over time, with the potential to take humanity to the stars. Jim Groth: I love how scientists get excited when something is disproven or questioned. Ooh, maybe we've been wrong. So I got a ton of comments on the latest episode about dark matter, dark energy, and it's a meme at this point. It's a trope. Someone will just storm in and go, you scientists just have to make up something called dark matter or dark energy. You don't know what you're talking about. And they skip off out into the internet. Who knows what they do? And I love this question or comment from Jim, because you're exactly right that a scientist loves to find out that they're wrong. They love to find out that they don't understand something as well as they did, because it creates a new opportunity for more discovery, more curiosity. It's more satisfying to understand the universe, nature, as it really is, not as you wish that it was. And yet I think the people who hurl that kind of an insult at scientists, oh, this thing that you've spent 15 years working on to get your PhD and do this research that you understand better than anybody else in the world, you're just making this up. You see something you don't understand, and so you're just filling in a hole, is really disrespectful. And we wouldn't say that to other people who have that level of expertise. Or maybe you would, I don't know. But I think Jim is exactly right that if you think that scientists in general, I mean, obviously there's bad scientists, there's bad people, but in general, scientists love to be proven wrong. They can't wait to find out that they now understand the laws of nature better than they did. And it's one of the things that I love about science. David Hall: if something the size of Mars hit the Earth back then, wouldn't it have left a signature crater the size of, I don't know, the Atlantic or Pacific Ocean? Who knows, maybe under all that water, one of them holds the location of the impact. For certain sized asteroid impacts on Earth, you get a crater. And if they're small, then erosion over time will fill in the crater plate tectonics will hide it and it will be lost forever. Pretty much the largest crater that we know of is in South Africa, and I apologize if I'm going to pronounce it wrong, Verdefort. And it is like closing in on 200 kilometers across. It was probably an impactor that was 25 kilometers across, much bigger than the one that killed the dinosaur 65 million years ago. This impactor absolutely created an extinction event on Earth that wiped out a lot of species. It's amazing that life can survive these kinds of impacts. But even so, a 25 kilometer across asteroid is nothing compared to a Mars-sized object. You're looking at 10 times bigger, 100 times bigger. So when a Mars-sized object, Theia, crashed into the Earth, it didn't cause a crater. It liquefied the entire planet, and it liquefied itself. And the two bodies turned into this sphere of molten rock that then had to cool down to the point that a solid crust could form on its surface. So it's no surprise that there's no visible crater, because it obliterated the surface of the entire planet when it crashed into us and formed the moon. So you won't find it because it's everywhere and nowhere. Nicholas Penryn: if the Big Rip and the Big Crunch have been ruled out, what's left? The Big Fluctuation? Enjoy the interview with Dylan Brout. I just want to give another vote to the interview that I just did with Dr. Dylan Brout. He is one of the researchers working on the Pantheon Plus research, where they mapped out 1,570 Type 1a supernova and measured the impact of dark matter and dark energy. I got the accuracy level wrong in the interview with him. It was a 5 sigma detection, and I said that was a 1 in 1 million chance that you're wrong. It's actually a 1 in 3.6 million chance that they're wrong. So the quality of the measurement that they did to sense the level of dark matter and dark energy, you could run those experiments 3.5 million times before it was a fluke that they were wrong. Absolutely amazing. So the Big Rip has been ruled out, that the amount of dark energy piling into every cubic meter of space is increasing. That would lead to the Big Rip. And so right now, maybe dark energy can push galaxies apart, but in the far, far future, maybe it could start to pull galaxies apart, could pull solar systems apart, pull stars apart, pull atoms apart, pull black holes apart, and eventually everything would be torn apart in the universe. That looks like it's not happening, which is nice. The Big Crunch is, well, if there was no dark energy and if the amount of mass was a little more, then maybe the expansion of the universe would reach some point and then everything would be pulled back in together to reverse the Big Bang. And that appears to be ruled out as well, that the universe, even without dark energy, would continue expanding forever. But now it looks like, thanks to the additional acceleration from dark energy, everything's just going to be carried away faster and faster. So what's left? Well, what's left is the heat death. That is the most likely outcome for how the universe ends. And that is, like, the name, the heat death, sounds really cool, right? It's like death by heat, but it's not death by heat. It's death of heat. So in the far, far future, every usable piece of energy will have run out. Every star will have died. Every black hole will have evaporated. Every planet will have cooled down to the background temperature of the universe. Every white dwarf will have fully crystallized and have no additional heat left over. That there will be no place that anyone can extract any further energy forever. So it'll be the death of heat and therefore the death of energy. And there will just be silence and quiet in this universe that is accelerating apart faster and faster, and nobody can survive because they are out of juice. And it's sad, and it's kind of terrifying, but it's also like a long way away. And who knows, maybe we'll think of something really clever to overcome the heat death. Or maybe we won't. And that's just the future fate of the universe. is to cool down and run out of energy. Zimmy 1958. How do you feel about the return to the moon? So you are talking about the upcoming Artemis 1 mission, which will eventually lead to the Artemis 3 mission, which will theoretically bring humans to the surface of the moon. Probably not by 2024, but maybe by 2026. It'll be soon. How do I feel? I love it. I'm excited, super excited to know that there are going to be human beings walking on the moon. We should have never left. I understand why we did, but I wish we hadn't left. I wish there had been a continuous presence on the moon since the 1960s until today. Then maybe we'd have a continuous presence on asteroids and on Mars. If you ever watch this great show called For All Mankind, the premise is that humans never left, the Americans never left the moon, the Russians never left the moon, and they're on to Mars by the mid-90s. And it's really cool because like the science is really good, but also they do a great job of projecting the technology forward. The ideas that had been proposed by NASA around that time, instead of just being canceled or sitting in some technical paper archive, they actually implement them in this show. I'm really, really excited. And this time around, I think it's inevitable. The costs are a lot lower than they were back in the Apollo era. Just our technology is so much better. We know how to go to space so much easier, so much cheaper. And you've got multiple parties that are trying to do it. So obviously, we know that NASA is hoping to send humans to the moon, but SpaceX with the Starship, like one of the things that Starship can do potentially is send humans to the moon. They're going to be supplying the landing system for the Artemis missions. But we've also got some private groups that are thinking about it. The European Space Agency has talked about building a base on the moon. You've got the Chinese who are planning to send humans to the moon probably by the end of the 2020s. So this time around, even if like we don't have all of our eggs in the NASA basket, we've got lots of options. And over time, my guess is that'll turn into 10 options and 50 options. And eventually the Indians will be able to do this mission, and the United Arab Emirates, and maybe even the Canadians. We could go to the moon. So yeah, I'm really excited to see humans return to the moon. I would love to see a research station on the moon, on an asteroid, and eventually on Mars. Michigan Mister, is life everywhere? It's everywhere on Earth. Wherever we find liquid water on planet Earth, we find life. Is there life across the solar system? We don't know. We know there's liquid water across the solar system. And so if in every nook and cranny of here on Earth, we find life wherever we find the water, then we should find it on these other planets. Now, even if the life didn't evolve separately on Mars or Europa or Enceladus, maybe there's some way that life can get from world to world, this idea of panspermia. That there are asteroids and meteors that are smashing off chunks of Earth and sending them off to Mars, or vice versa, because it really looks like Mars was a much more habitable world before Earth had cooled down. While Earth was still that molten ball of rock, Mars probably had oceans and weather. And even a magnetosphere. So it could very well be that life formed on Mars first and then shifted over to Earth. And so if we do find life on Mars or Enceladus, on Europa, it could be related to us. And so if it is related to us, that still doesn't tell us if life is everywhere. Is life in other star systems? The answer is we don't know. The default answer is to say, of course it is. How could it not be? The universe is big. The universe is old. All of the chemicals for life should be everywhere across the universe. It should be everywhere. And yet we don't see any sign of it. And so the question is, where is it? And this is a mystery. And one that hopefully we're just within capability of starting to answer. James Webb has the kind of capability on board to detect the presence of chemicals in the atmosphere of other planets. It could detect pollution from an alien civilization in another planet. And if James Webb can't do it, then a follow-on telescope like LUVOIR would be able to take things to the next level. And, there's been an estimate that LUVOIR, when it comes online, this is going to be this giant telescope. I mean, it won't be the original 9 to 15 meter telescope, but maybe it'll be a 6.5 meter telescope like Webb, but it'll be equipped with a star shade that will allow it to block the light from the star. That it will be able to look out and study the atmospheres of enough planets around us in enough star systems around us to tell us to like a 95% level of accuracy whether or not we're alone in the universe. So we don't know the answer, but we're really close to being able to answer it either in the positive, like we have found life on another star system, we have found life on another planet, or in the negative, that we have explored a region of space that is large enough around us to tell us that we're probably alone in the universe. In the classic words of Arthur C. Clarke, two possibilities exist. Either we're alone in the universe or we're not. And each one is equally terrifying. Bomdia, will there be another DART mission like the last one? There are no plans to send another mission to crash into an asteroid like DART did to try and shift the orbit of the asteroid. But like the DART mission did an incredible amount of value to scientists. We talked about the DART mission in a recent Space Bites episode, how like the amount of time that it knocked off the orbit of the asteroid that's orbiting the other asteroid was 30 minutes. And that was like 3 times bigger than astronomers' best hopes on how much of an impact that it would have. Pardon the pun. So now we have a data point. We know that if you have an asteroid of a certain kind of mass and you smash an impactor into that asteroid, you can change its velocity by a set amount. And so if we detect that there is an asteroid on a collision course with Earth, we can calculate the size of the impactor that would be needed to shift it out of a dangerous trajectory to stop it from hitting Earth to missing Earth. We've never known that before. We've always had these estimates, and as you can see, the estimate was off. The way the asteroid behaves is different than the theories had predicted. That's huge, and it's something you can put into your calculation box if that asteroid ever shows up. But there's a lot of other work to be done. The European Space Agency is sending a mission called Hera that's going to be doing follow-on observations to really take a good look at the damage that was done to Dimorphos. We've got potentially a mission that's going to go to a completely different class of asteroid called Psyche. You're going to look at this metal asteroid and try to see how does the gravity field of an asteroid that is completely made of metal change. We would need to study more comets because they're going to be more dangerous. Comets can come out of nowhere. They're coming very fast. You have no warning. What would it take to move a comet? So I think engineers got enough information from that one impact to crunch on for a long, long time. And there's a lot of other scientific questions that we would need to answer. But I mean, I find that whole process really encouraging. We've talked about this in the past. Like, what's the best way to stop a killer asteroid? Do we need to launch nuclear missiles at it? Do we need to send Bruce Willis and a team of deep rock drillers to put a bunch of explosives to break up the asteroid? Do we need to paint it white so that the radiation from the sun shifts its orbit? Do we have a gravity tractor hover nearby, slowly shifting it off its trajectory? No, we just take metal and fire it at the asteroid and it does the trick. We just have to make sure we fire enough metal. And if 500 kilograms was enough to move a asteroid that big, that significantly, we just need more metal if we're in a more dangerous situation. So no, I think we're good. It's awesome. If you like my answers to your questions, as well as the other things we do at Universe Today, consider joining our Patreon club. You'll get an ad-free experience on universetoday.com for life, even if you unsubscribe. You get ad-free videos, early access to interviews, as well as other perks that are exclusive to our Patreon community. And thanks to everyone who's already subscribed, and welcome to our recent newcomers: William Johnson, Prakasha Productions, Simon David Parton, Michael Kevershin, Edward Ray, Jerry McMurray, The Nocturnist, John Graves, Todd Wagner, Thomas Dudley. Join the club at patreon.com/universetoday. Kim Draper, are there any missions being planned that you know of to try to clean up the debris orbiting Earth? So now we have thousands of satellites orbiting Earth. We have thousands of booster rockets. We have debris. Satellites have crashed into other satellites and caused smaller pieces. It's estimated that there are like 100,000 objects 1 centimeter across or bigger orbiting in low Earth orbit, it's a busy, busy place. And over time, more and more satellites will be launched up, and they can just contribute to this space junk problem. And if they crash into each other, then we'll get more and more debris, and it can get pretty scary. So what's being done about this? There's the easy solution and there's the hard solution. The easy solution is that you clean up after yourself when you fire a rocket or you fire a satellite. So, for example, you've got a booster rocket. Like when a satellite is launched, there'll be an upper stage booster. And the upper stage booster is there to put the satellite into its final orbit. But in order to do that, the booster has to pretty much get into the same orbit as the payload. And so now you've got the satellite payload and you've also got the booster orbiting at the same time and place. That's one useful satellite and one piece of space junk. So the plan now is that people have to come up with some way to bring their booster back down into the atmosphere to make it crash up. You can deploy a drag chute behind the booster. You can deploy some kind of tether that interacts with the atmosphere of the Earth and drags this booster back down. The other point is that you have to add some kind of end of life for the satellite. So as a satellite is reaching the end of its mission, 5 years down the road, whatever, when it senses that it's about to die, then it has to have some way of deorbiting itself. So it can, again, deploy a drag chute, it can release a tether, and then it will interact with the atmosphere and it will spiral in and burn up in the atmosphere and be gone. That is good housekeeping. That is cleaning up after yourself. But there's a lot of debris. I mentioned the 100,000 objects bigger than a centimeter. I'm sure that number is even smaller than it really is. How do you get those? That's tricky because each one of those pieces of debris is on its own special trajectory. Like it can be going 28,000 kilometers per hour around the Earth on an individual trajectory that no other satellite is following. And when you imagine, like all of these things are just buzzing around the Earth, and you would have to launch 100,000 rockets, each of which was tasked to grab one chunk of space debris and then re-enter the Earth's atmosphere with it, which is crazy. And just think about the amount of space debris your rocket is going to create as it launches. You're going to have the upper stage booster. You're going to have the satellite. It's going to grab onto the piece of debris. And then together, they're all going to make their way. Like it's impossible. So the one idea that's been thought to actually remove space debris that I really like is that you set up some kind of orbital laser system that is orbiting around the Earth. And as a piece of debris is flying past, it fires the laser at the debris and vaporizes it a tiny little bit in a way that reduces its orbit. And over time, the laser sitting there is it's just picking off every single piece of debris that's going by, changing its targets one after the other, and they're all getting friction. And over time, all this debris just starts raining back down into the atmosphere. But who wants to let some country put a incredibly powerful laser system into orbit that can shoot the Earth as well or destroy other people's satellites? So there are diplomatic issues that have to be ironed out, but I think that having some kind of debris removal system in orbit is a good way to go. And the sooner we can get on that, the sooner we can make sure that the space environment is as clean as the Earth environment, he says ironically. Sledge Bear. If we were to put a lot of space telescopes in orbit around the L2 point, could it function as an event horizon telescope? Yes, if you were trying to build a space event horizon telescope. So the Event Horizon Telescope, this is the worldwide network of telescopes that was used together, radio telescopes that work together to take an image of the event horizon around supermassive black holes. We've got an image of M87, and we've got an image of the supermassive black hole at the heart of the Milky Way. And they worked because when you separate any kind of telescope, when you separate them, those telescopes can act like a single telescope that is the size of the space in between them. And this is a technique called interferometry. And so if you put a telescope at the North Pole and you put a telescope at the South Pole, and they look at the same object, they can work together to produce an image where it makes a virtual telescope that is the size of the entire planet Earth. Now, there's a pile of caveats there, and I'm sure people are watching this are ready for all my caveats. So the first one is you have to get the timing perfectly down to the wavelength. So if you can imagine, there are radio waves coming from some distant object, and you're going to have two radio telescopes looking at the same thing. They've got to be seeing the exact same wavelengths of that object. And the way they do this with the Event Horizon Telescope and other radio telescopes is they can do this after the fact. They have really accurate clocks on the telescopes. They track when they were recording the signal, and then in computer, they then line up the signals until they make sure they get the same wavelength. And then they're able to then get that virtual telescope that's the size of the planet. You can get objects that are very bright. You get a resolution, but you don't get additional brightness. So you get if you're going to look at a very dim object, all you get is the magnification of the two telescopes put together, but it's the resolution for very bright objects. That's where you get that separation. And so that's why they looked at the event horizon of a black hole. It's a very bright object. You can see the quasar or the hot gas around a supermassive black hole millions and millions of light years away. It wouldn't work with a very dim object like a brown dwarf or something like that. So you're planning to take this constellation of telescopes and you're going to put it out at L2, the L2 Lagrange point. This is the point that is on the far side of the Earth from the sun. This is where James Webb is, and it is gravitationally metastable. And so with a little bit of propellant, you could put a spacecraft into that area. And you could put multiple spacecraft into that area. And it's not a point because the distance from the Earth to the sun is changing over time. You've got the gravitational interaction of the moon, the planets. L2 is a zone, and you're trying to use your propellant to keep your spacecraft in the zone, and you are orbiting around that region. And so you could have multiple spacecraft that are orbiting around in the L2 region together, and they are acting like a virtual telescope, an interferometer working together. They have very accurate clocks on board. They send all their data back down to Earth, and astronomers on Earth can calculate the information. But you could also have one spacecraft out at the L2 point, and you could have a Earth-based radio telescope with an accurate clock, add those together, and now you've got a telescope that is the size of L2 to Earth, like 1.5 million kilometers. You built a telescope that is 1.5 million kilometers across. You could take three radio telescopes, put one at the L4 point, L5 point, and one at the L3 point, which is on the other side of the sun. They could form this giant equilateral triangle, and you would have a telescope that is 300 million kilometers across. You could put a telescope on Earth. You could put a telescope at Pluto. The challenge, of course, is the amount of time it's going to take, the amount of data that you can send home. When you think about the Event Horizon Telescope, they had to fly hard drives filled with data to a central processing area where they could crunch the numbers. And so it would be very slow to try and communicate the data from some satellite system. But it is theoretically possible to do a radio telescope. It has been done. There was a radio telescope that was in orbit far away from the Earth, and astronomers were able to add the signal from that telescope to the telescopes on Earth to create a radio telescope that was bigger than planet Earth. And I wouldn't be surprised in the future that we see a radio telescope get launched to some place in space, high orbit around the Earth, out onto the, attached to the surface of the moon, out at the L2 point, on Mars. It's just that the challenge is sending that data home so that you can crunch it on a computer after the fact. But wherever you send a telescope, the farther you can get it away from you, the better your resolution is going to get. You still need to look at very bright objects, but it just becomes higher and higher resolution. Maybe we could see the photon ring around a black hole, whatever is the final thing that we could see. Linda Jerka. So if everything cools off in the end, what happens to dark energy relative to the definition of energy? The term dark energy is a bit of a misnomer, and it's unfortunate because it could very well be neither dark nor energy, in the same way that dark matter is probably neither dark nor matter, and that black holes are neither black nor holes, that Big Bang, well, okay, Big Bang is big, but it's not a bang. So a lot of these terms in science, they stick, but they aren't necessarily accurate. And a lot of times people get grumpy because they don't like the word, but they don't understand that the word doesn't really match the thing. So anyway, dark energy is this accelerating expansion of the universe. It seems to be some kind of constant outward pressure that is pushing away the galaxies faster and faster away from each other. And as the universe continues to expand, or as the universe continues to get less dense, you've got more and more space opening up in between the galaxies. And for every cubic meter of space in the universe, there appears to be a set amount of dark energy that appears with it. And so if you have 1x dark energy for every cubic meter of space, if you have 2 cubic meters of space, you now have 2. 3 cubic meters of space, you now have 3. And so while this expansion of the universe is happening, you've got more space opening up and more dark energy. So this dark energy is constant. And that is different from energy. You know, when you have the energy from heat, the energy from gravity, you've got velocity, you've got stored energy, you've got kinetic energy, you've got all these different forms of energy. And so the heat death is when none of these are usable anymore. Dark energy will still be going strong. It will be, every second that goes by, there will be more dark energy in the universe than there has ever been. And 1 second later, now this is the new record for the amount of dark energy. And there's no reason to believe that dark energy would stop. If you take the observable universe, now over time, the observable universe gets bigger because we can observe more of it. But the amount of matter that's going to be in the universe is going to be roughly the same. The amount of dark matter is going to be roughly the same. But the amount of dark energy will just keep increasing and increasing and increasing as there is more universe. And eventually, if you were to calculate the amount of dark matter versus dark energy versus matter in the universe, it'll be 100% dark energy, or it'll be 99.9999 dark energy, and then a little bit of dark matter, and then a little bit of matter, and that'll just be the future. Johnny G, what are your thoughts on the Viking mission and NASA's refusal to follow up on them as it concerns positive signs of life? In the 1970s, NASA's Viking mission landed on Mars, and on board they had an experiment that was really clever. They had some local nutrients and water on board the spacecraft. They scooped up some samples of Mars. They put them into a little capsule. They put in water, nutrients, and then they detected the gases that were coming out of the experiment. And things happened. And people attributed there must be life on Mars, that there was some kind of bacterial life in the regolith on Mars that was wet and for the first time in a billion years and had food for the first time in a billion years, and it just went to town coming out of suspension. But there was controversy. The results were inconclusive, and so people would argue back and forth about whether or not this experiment was successful. It's like the worst kind of scientific result that you can possibly hope for is that your results are inconclusive. You can't be certain that what you saw was life. You can't be certain that what you saw wasn't life. You don't know. And I think the idea was solid. And I wish that the response had been, let's try to make a version of this experiment that is conclusive. Let's break down the variables that are participating. Let's send InSight. Imagine if InSight had 20 chambers on board and it could scoop up bits of regolith, drop it in, isolate the variables. One thing, it could dump the chambers overboard, wash them out, expose them to radiation. I don't know, whatever. Like, I feel like they could have figured out a way to make that experiment, because you know that when we have samples returned from the surface of Mars, scientists here on Earth are going to perform some version of that experiment. They're going to take the samples from Perseverance, they're going to crush them up, they're going to put them into some sort of solution, they're going to add nutrients, they're going to add heat, they're going to see what happens, and they're going to look under a microscope and try and figure out what's going on. So I think that because that was inconclusive, it sort of spooked NASA, and they wanted to go a different pathway to build up the case for there being life on Mars. That's why we saw the Spirit and Opportunity were there to search if there was ever water on Mars. And then it was Curiosity's job to find out if there was water on Mars for long periods of time. And now it's Perseverance's job to see if there was the conditions for life on Mars in the past or in the present. But we're still not getting back to that question of, like, is there life in the soil? Can you just add nutrients and get life going again? And it's too bad, I think, because it's a fascinating idea, a relatively easy experiment to run, and with lessons learned, I'm sure we could figure out a way to make it less uncertain. So that's how I feel. I feel like I love ideas that are out there, that are Hail Marys, when you're like, oh, maybe this would work. Let's try this out. And sometimes you succeed and sometimes you don't. And I think that people are very skittish when the results they're not a slam dunk right away. You need to iterate. And I wish there was more iteration on a lot of those most interesting experiments. I think about I'm always such a fan of JAXA, the Japanese Space Agency. When they did their mission, their Hayabusa mission and their Hayabusa 2 mission, they had just a wonderful collection of great ideas. They had a rover designed to flop around on the surface of Ryugu. They shot it with an anti-tank weapon. They snorted up the debris that came out of it, and they brought it back to Earth. And scientists have made some really fascinating discoveries about what they found there. So I think when the Mars sample return mission brings those samples back from Mars, we will get the data that we're hoping for. Because one of those samples, it's just as easy to collect up a bunch of regolith, keep it in a tube, bring it home to Earth, and you will get the same you'll be able to run the experiment, but now you're doing it in a lab on Earth. So hang tough, wait for the Mars sample return mission. We will get our answers. All right. Those were all of the questions that we had this week. Thank everyone who asked them in the YouTube comments. Thanks everybody who showed up for the live chat. Again, we do this every Monday at 5 p.m. Pacific time. There's going to be an event for the next one somewhere here on the channel. So subscribe to the channel, click the notification bell so that you will be notified when we go live next week. All right. We'll see you next week. If you want to stay on top of all the important space news, join my weekly email newsletter. I send it out every Friday to more than 55,000 people. I write every word. There are no ads, and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There, you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Josh Schultz and Andrew M. Gross, who support us at the Master of the Universe level. All your support means the universe to us.